Hi, my name is Sam Romano, and this is my Physics 2211 Lab 2 video report on projectile motion. And in this lab, I recorded the two-dimensional motion of a thrown paper ball, analyzed it in tracker, and compared the observed motion of two tracker glow script models, one with gravity only and the other with gravity plus air resistance. In this presentation, I will first give a brief introduction and preview of the results, explain the fundamental principles and the computational models, uh, describe the experiment and procedure, compare the model predictions to the tracker data, discuss the possible sources of error, answer further questions, and finish it with conclusions. And my main result preview is that both models match the data closely, but the gravity drag or gravity plus drag model matched it slightly better, and the drag effect in my trial was small, so the two predicted curves were somewhat similar. So this lab is based off Newton's second law, or the momentum principle, where the net force calculates the object's momentum and velocity to change over time. The two forces used in the model are gravity and drag. Gravity acts downward in the negative y direction and provides a constant force on the ball, and drag acts opposite of the direction of motion and increases it with speed squared, so it can be reduced to the net force and change of the acceleration over time, which means in the gravity only model, acceleration is determined only by gravity, and in the drag model, acceleration changes as the velocity changes. And to build the computational models, I used tracker data to estimate the initial velocity, and then use numerical update equations in GlowScript to update velocity and position step by step. The code updates velocity using Newton's second law, and then updates position using the new velocity over a small time step. For the gravity only case, I set the drag constant b to 0. And for the gravity plus drag case, I set the constant to b equals 0.000020. For the experiment itself, I recorded a video of a thrown paper ball moving across the screen with a stationary camera. In tracker, I calibrated the scene using a known length, set the x-axis along the floor, and placed the origin directly below the initial position of the ball. When I tracked the ball frame by frame to extract position versus time data, and then use those models as inputs for the GlowScript model. And then I compared the observed and prediction motion using a spreadsheet graphs. So the next two slides show the actual GlowScript codes and screenshots that I use, including the tracker-based initial conditions, time by time step, and force calculations. In this specific slide, the gravity only code, the drag constant is set to b equals 0, so the net force is only gravity. And the graph on the right shows the position versus time and velocity versus time for each model. And in the gravity only model, the velocity graph is more linear, which reflects more of a nearly constant acceleration. And for the gravity plus drag code, the constant is b equals 0.000020. So the net force includes both the gravity and drag. And the drag opposes the motion and slightly reduces the net force. So the motion changes very slightly, and the prediction fits the real trajectory a little better. And you can see this in this graph because the fitted drag value is small. So the difference between the two models results is very small in this trial. And on this comparison graph, they're all plotted together. And both models follow the observed motion closely, but you can see the gravity plus drag fits it a little bit better. And physically, this means air resistance was present, but it was not large enough to uh, create a big separation between the two predictions. So the data supports the idea that drag affects projectile motion, but in this trial, the effect was small since the paper ball was so small. And possible errors or sources of errors can include camera alignment and perspective error, tracker marking and calibration uncertainty, and ball shape or spin change, the drag during the flight. These can affect the measured positions, which can also affect the fitted drag constant. And this kind of explains the small differences between the data and the model, the observed model. So for the further questions, terminal velocity happens when drag force balances gravity. So the net force becomes 0 and acceleration becomes 0 and the velocity becomes constant. So the gravity only model does not predict terminal velocity. And in my experiment specifically, the drag model also did not clearly reach terminal velocity because the motion was very short and the drag effect was very small. So the velocity did not level off within the recorded time. A better experiment to observe this terminal velocity would be dropping the same paper ball from a much higher height and tracking the velocity versus time until it plateaus. If the object were thrown, and what happens if the object were thrown straight up at the same initial speed, the time to reach the ground would be longer than the original experiment because it would first rise slow to zero velocity, then fall back down, and that's adding extra flight time. So in conclusion, the gravity plus drag model matches the data slightly better than the gravity only model. However, the fitted drag effect was small, so both predictions were very similar. This lab shows how Newton's second law can be used to model both ideal projectile motion and more realistic motion that includes air resistance. Thank you.